The most elementary behavior of an organism is an orientation with respect to a stimulus source. The animal may turn or move away from the source of stimulation. Jacques Loeb called this orientation as tropisms, but later on the term taxis singular, which was preferred in order to separate the behavioral response of animals from growth responses of tropisms occurring in plants. Taxes may be positive or negative with respect to the stimulus the animal turned toward or away. A positive phototaxis is an orientation toward the source of a light. Similarly, the terms chemotaxis chemical, geotaxis gravity, thigmotaxis contact or touch, rheotaxis current, galvanotaxis or electric current, phonotaxis acoustic, and anemotaxis wind are common examples. A taxis is often called forced response because the organism is governed by the directional nature of the stimulus in a mechanical way, just as a bulb lights soon after the switch is on. Taxes seem to be present in all metazoa and are readily identifiable among the invertebrates and some vertebrate larvae and embryos. Some important features of taxes are automatic character, simplicity of integration, and low at a psychological level. One of the most important features of the taxis is that it is inhibited and exhibited only by bilateral symmetrical animals. Example, if an earthworm, equal stimulation of right receptors on both sides result in equal excitation of the locomotor musculature so that the animal moves in a straight line away from the source of light. When the receptors on the left are stimulated more strongly by a short light beam, the muscles on the opposite right side contract more strongly and the animal turns away from the light. In an animal, another example, a positively phototactic insect has been blinded in one eye will move around in circles as if trying to maintain equal stimulus intensities on the left and right receptors. Effect on blinding on one side, phototaxis in fly, phototaxis in bee, left eye blackened. The circus movements to the right in the first few tracks later gradually straighten and the animal eventually orients directly toward the light. Beside the above mentioned different types, taxis can further be the following types like clinotaxis. This is a process of successive comparison of the intensity of a stimulus in one side of the body and then on the other. Clinotaxis is found in a number of animals including euglena. Example, the head of a maggot larvae of housefly is provided with light sensitive receptors capable of registering different light intensities but not by obtaining any information about the direction of light. As the maggot crawls along it moves its head from side to side, testing the intensity of light on each side of its body. Suppose the intensity on the right side is greater than on the left, then the larva tend to change its course and crawl more toward the left, away from the light. Next one is the tropotaxis. It is characterized by a straight course toward or away from a source of stimulation. Clinotaxis is a process of successive comparison of intensity of a stimulus on one side of the body and then to the other, but tropotaxis is characterized by a straight course toward or away from the source of stimulation. There is a wavy course in clinotaxis. Here, that is the straight course. Suppose an animal can make a simultaneous comparison of the intensity of stimulation received from two or more receptors and can make out a balance between them. This all can be achieved by tropotaxis, a bisensor system. Example, a pill worm louse with a pair of compound eyes on the head moves directly toward the light, but with one eye it moves in circles. It shows that the animal normally relies upon the balance of the stimulation from its two eyes. Often the animal takes a median course between the two light sources but then towards one. If by change the animal finds itself facing a particular light source, it will head towards it, ignoring any source from the sides. So, teleotaxis, it is a directional orientation without having to compare the stimulation from two receptors. It is exhibited by all animals having eyes. In this case, an eye is with the lens and some sort of retina containing a number of receptors, the rods, cones, etc. And the information and position of image provides knowledge about the direction which is necessary for orientation. Teleotaxis may thus be defined as a direct orientation movement to light. By menotaxis, this is the orientation may or may not be accompanied by locomotion. The animal orients itself at a constant angle or dorsally or ventrally in response to stimulus, particularly light. It is also called light compass reaction. For an example, ants usually follow trails to and from their nest and use a variety of cues or hints, but chief among them is the light. Ants often orient themselves and move in some direction with respect to the source of light. Now let's learn about the next one, that is kinesis. Like taxis, kinesis are forced responses in the sense that the stimulus intensity controls the behavior of the organism. But many animals, such as protozoans, which are not bilaterally symmetrical, show an orientation and can move toward or away from the source of stimulation. Example, in its simplest form, Euglena moves toward a light source by wandering about until it is oriented in a way that its light sensitive stigma receives the strongest illumination. So the phototactic orientation in Euglena, which swims in its characteristic spiral motion toward the source of light, upon reaching point 2, the light is changed to be due to asymmetry of its light receptor. Euglena eventually changes direction and swims towards the new light source. Similarly, the velocity of locomotion of the flatworm planaria is proportional to the intensity of light, and this kinesis causes planarians to spend their time in dark places. The kinesis can be following two types. Orthokinesis, a type in which there is a relationship between intensity of stimulus and speed of locomotion, as shown above by the example of planaria. Clinokinesis. In this kind of kinesis, the rate of change of direction is related to the light intensity in case of clinokinesis. Next one is an example of clinokinesis. Another flatworm also prefers to aggregate in dark places. Upon entering an area of high illumination, the rate of turning increases considerably. But if the animal remains in light conditions, the turning rate gradually falls. This adaptation has been shown to be necessary to enable the animal to seek darkness in conditions where there is a gradient from high to low levels of illumination. Clinokinesis is also exhibited by a saw bug or wood louse. In a lighted area, this insect simply walks faster than in shaded area. In low intensity illumination, locomotion slows down or may stop temporarily. Under such conditions, several bugs will eventually collect in a shaded spot. In the end, it will be concluded that in both the cases, taxis and kinase, the directionality of the stimulus energy is responded to in a direct fashion. A taxis orientation involves higher level of sensory and central nervous organization as compared to kinesis.